for the predicted IQ for each student?
103.
103. What about Bernard?
103.
103. What about Christy?
103.
Oh boy. What about Deja?
103.
Is your last name Boo?
What about Eldon?
103.
Okay, so here's the deal. We just did this predicted IQ. As a review, in statistics, how do we denote that something is predicted? It's a hat, right? We'll put the hat on it. So Y hat is a predicted value. Very important to remember that. Now, the veteran noticed the equation written on the board for the AP statistics room. IQ is equal to 16 times, this should be times, GPA plus 57.3. Realize that GPA can help her make better predictions. Okay, so then she takes their GPA and she's going to plug it into this formula. So what did you get when you performed this formula on using the line of best fit? What did you get for Adam?
86.1.
What?
86.1.
Yeah.
Yes. What about Bernard?
95.7.
Oh.
What about Christy?
103.
What about Deja? Deja?
111.7.
Okay, and then Eldon?
118.1.
So here's the thing. This is a real life example where we have a residual. We have a residual versus actual, right? So here's the predicted, here's the predicted. So we're looking at these values. So flip the page. Sorry, the truth seeker at the bottom. She found out the truth. So when she finds out the truth, what do you notice about those values? What? So check it out. Found the truth. Thought it was 85, it was 86. Thought it was 95, it was 95. Thought it was 103, it was 110, 111, 105, 118, 120. Okay? This is how life works. This is the beauty of stats. Stats is making a prediction and checking against actual data. So flip the page. So here's what we're going to do. Now we're going to calculate some residuals. So in this top chart, it's saying which counselor made better predictions. Is that really easy to discern? It is?
Yes.
Okay. Okay. Let's find out. So yesterday we talked about, right, distance from a line. And when we have residuals, we take the square distance. What we're going to do right now is we're going to measure each counselor's predictions and find a number. Because statistics, we like a number, right? We're going to put a number on it, like how good was their prediction, which one was better, and how much better. So what I'd like for you to do is, I would like for you guys to, you can divide the work on this, okay? So divide the work, fill out these next two boxes to find the sum of the squared errors for each of those two counselors. So here's what we've got, right? So, oh, I gotta roll this down. So basically what we did was we took their prediction and we took what their actual was and predicted. So we did residual equals actual minus predicted, and we took the squared error. So somebody help me out. Why do we square the error?
So have positive and negative errors.
Yeah, so for example, right, so if this was, 103, so this was a minus 18, and our squared error would be 324, and then this one was 103 minus 8, 64 was our squared error. This one was 103 and 7, this is 49. Squaring the error allows them not to undo one another. So if I just added negative 18, negative 8, and 7, I'd all of a sudden have an error of much less, like a negative 11, right? Well, negative 19. But that's not actually my amount of error. My amount of error was how much I was off. So regardless of above or below. So what was the sum? So we fill the rest of the same. What's the sum of my squared errors here?
7.
So accounting for above and below and squaring it, 730. When we do all this down here, the counselor, the veteran, So use the line of best fit. What'd you get as the sum of the squared errors? 89.89. Okay, so the question is, who did better? You know the answer to this question. Who did better?
Number 2.
Counselor 2 did better. But the question that we actually want to ask in statistics is how much better? Okay? And so how much better? And how much better is better? And what is a metric for better? And like, what does the error mean? Okay, and so let's take a look here for a second. So the veteran did better. Why? So her sum of squared errors (89.89). Putting some context around this, right? Writing with context. Was less than the sum of the new guy. Right? Less than the sum of the new guy. So it's 730 versus 89.89. So here's what we're going to do. Percentage improvement. 730 minus 89.89 over compared to our original. So we end up with 640.11 over 730.
Wait, is percentage improvement just like new over old? Like new minus old over old?
Percentage improvement was how much change compared to our original.
Okay. I know which one is the
So from guidance 1 to 2. So if it's from one to the other, you compare to the one you're coming from. Okay? And so as we look at this, we could also find each counselor's typical error. What do you think that means by typical error? The average error. Why would we want to know that?
you can apply it to like each.
2 other counselors.
You can know like how far he was off, so you can get more accurate.
Okay. So let's look. So what would you use to do that, do you think?
Square root it and divide by 5.
Why'd you square root it and then divide by 5?
Because the sum of square root is squared, so then you need to undo that, and then you need to undo that it was all of the stuff added together.
Okay. So what should you do first?
Square it.
What do you get when you do that?
I'm gonna do all of it.
Mm-hmm.
I got 1.89. Like for
Anybody do it differently? Pull out your calculators.
Well, I would.
Pull out your calculator. I would like for you to actually do a correlation coefficient on this data. Okay? So let's actually run, find our correlation and that kind of thing. So you get your 2 lists together. I'm going to show you some statistics here. So put GPA into one list, put IQ into another, fill in these values. Let's see what we come up with.
The first one, wouldn't you divide by 5 first, then take the square root?
Now hold on a second. Take a look at this. I'm going to open up my. Do you see a connection here? See what I'm getting at? Plug in my camera. Are there any values that you find repeated?
Oh, 87.
0.877. You see it? So 0.877 is repeated. Where's it from? The percent improvement. Okay? How do those correlate? That honestly, that's the question. All right, so what are these values measuring? So let's take a look here. That's what we're exploring. I want to talk about the algebra behind this because if one value up here, this 0.877, so our squared value is 0.877 here. What is this? What's our R value?
36.
0.936. So is it strongly correlated or?
Yeah.
Okay, fairly strong positive linear association. So S, let's talk about the standard deviation here for just a minute. S is stood for standard deviation, right? So let's take a look at this algebraically here for just a minute. It's asking you for the typical error. The typical error. So how do we algebraically do that? Well, what does 89.89 represent? The sum of the squared errors. So if I take 89.89 and I divide by 5, I get the typical amount of squared error per person. Okay? So then I'm going to take the square root of the whole thing. So what do you get when you take the square root of the whole thing?
4.24.
Okay, 4.24. Okay? Here's what I'm telling you. That's going to go there. But do you see that value?
No.
Does your calculator spit out that? What value does your calculator spit out?
We don't have that.
Where do we get this value?
Somewhere. Do you plug in like the residuals and stuff like
Aha. Okay, so what are we measuring with S? This is the point of the whole thing. What are we measuring with S? It's standard deviation. Standard deviation of what? The residuals. Do you have a list that represents residuals right now? Make a list that represents residuals. Do you have it on your paper already?
Yes.
Yes, you do.
Do we put it on our calculator?
For which
I would.
one? Yeah, for which one?
Counselor 2.
Yeah.
Gigi.
Okay. So what's the difference between when you do line regression and you calculate that versus doing stat, line regression, and then for the store reg thing doing
Wait.
R1 stats
So did you get?
or
So when you do the Y1 in there, it puts it into Y1.
I just plugged it into L.
So that you can graph it.
To get like
If we're not concerned with graphing it, we don't need to store the regression equation anyway. Just one. So we want the list of residuals. Where are we going to get standard deviation of one list?
one bar stack.
One var stats. Okay, so under the calc menu under stat, you're going to do the one variable statistics of just list 3.
sorry, I forgot how to switch between lists again.
So look at your numbers 1, 2, 3, 3 keys above them. So you're going to do like a second.
So for capital S is like of a population of a sample, and then the other one is for a population. But like this one, because there's not that many people, we do that one. Right?
So here's the question. Do you even see the value 4.24 on your list?
Yeah.
Mm-hmm.
It's 4.239.
Okay. What's the other value?
4.74. Because they did n-1 instead.
Okay.
Like how do you know which one to use?
How do you know which one to use?
This is a sample, it's not population.
Will you always use one of them for these types of equations, or does it matter on how much data you have?
It's a good question. We're going to answer that question later in this course. So we're gonna come to a point where we are talking about is the sample size large enough to represent a population. This one is not.
So it is 424?
4.24. Okay? 4.24. So, what did we just do? What did we just measure?
The typical error for a student, for like one student.
What the standard deviation measures?
much
Just a little review here.
How much a data value is
The typical amount of it.
Yes, how much a data value typically varies from the mean, right? And so our typical error, our error typically varies from the mean of the errors by 4.24. Let's break this down a little bit. Okay? Standard deviation of the residuals. Standard deviation of the residuals, denoted S. Here's our interpretation. If they said interpret this value in context. The actual Y context, the actual IQ is typically about what? There's the number that goes in there. S, so standard deviation, away from what? So this is the question that I'm asked, that we're trying to figure out. This is the thing we use. Not necessarily just the regression, but you're on the right track. You're so close.
Line of best fit.
It is the line of best fit, but if I'm comparing one data point being a certain amount away from
the predicted value?
the value predicted by the least squared regression line. Do you understand the difference there? So don't just say from the line, because the line is a bunch of points, right? So if I've got this point and this is the predicted one, it's not the same distance from here as it is to here. But what we're comparing using the standard deviation is how far is it from predicted to actual? And we're taking that, so that's the measurement. So away from the number predicted by the least squared regression line. So how far, so a given IQ, the actual IQ is typically about 4.24 away from the number predicted by the least squared regression line.
When we're writing this response, are we allowed to abbreviate it?
LSRL, that's a standard. That is a standard statistics known thing. Okay. Coefficient of determination. Okay, so we're going to talk about the R squared value here. So here's our interpretation. About R squared percent. So that's the R squared percent of the variability in Y context is accounted for by the least squared regression line.
R squared.
This is where you put in your R squared value.
Is what for?
All right, so this right here probably doesn't make a whole lot of sense. Am I right? Okay, so let me explain it to you in this way. Okay? Let's say, for example, we did a least squared regression line that involves pizza toppings. Okay, pizza toppings. So what we did was we plotted, I'm going to erase this part for just now. Let's say for a second that we plotted the cost of a pizza in association with the number of toppings, right? So as number of toppings goes up, what happens to the price of the pizza?
Goes up.
All right, so I guess there's going to be a pretty strong association there, right? You know this. You go to a pizza place, you're like, oh man, pizza's only $10. Well, if you want anything on it, $3.50 per topping. What? Or you can order one of our custom pizzas. Okay, anyway. So we kind of understand this. So let's say that we pizza toppings, and this is the number, and this is cost of pizza. So let's say we draw a least squared regression line here. Okay? Say the toppings cost different. Well, okay. So we draw this least squared regression line. What did we just do? Well, we just drew a line that represents a good average, right? It's the best, the smallest amount of distances here, right? In general. Okay, so that's a pretty. So then I told you that my R squared value for this particular regression was 80, so 0.867. So what does that mean? Let's interpret it in context. 86% of the variability in pizza cost can be accounted for by the least squared regression line, which is modeling toppings versus cost. So what is the variation in pizza cost? What does that mean? What is variability in pizza cost?
Oh, different toppings?
No, variability in pizza cost is some pizzas cost more than others, right? So that variability, the amount of variability of types of pizza is accounted for by this least squared regression line.
What do you mean accounted for?
So this is the question. What does it mean accounted for? Consider this for a second. Let's say this is the pepperoni pizza. Okay, this is just the cheese pizza, or whatever it is, toppings go up. So cheese pizza, pepperoni pizza. This is Papa's Supreme. This is the super mega combo. This is the super mega combo without pepperoni. Okay. What is causing the variability? Why is this pizza joint allowed to charge more? Why does it seem reasonable for them to charge more? The number of toppings goes up. But those toppings don't all cost the same, right? So the price of the pizza doesn't go up linearly. You see where I'm going with this? And so the variation here, it's kind of artificial, right? Because the least squared regression line in this context doesn't really represent anything. It's if we flattened everything out and said, what if every single topping cost the same? Does that make sense? So if every single topping costs the same, that's the least squared regression line. Because it has a slope, it has a y-intercept. Well, y-intercept is the base cost of the pizza, right? What would the slope represent?
How much of the pizza price costs
Per topping, cost per topping. So track with me here. If it doesn't go up linearly, there's a variation. That variation represents what?
How far from the predicted?
How far from the predicted that it is, but in the case of the pizza topping, what does the variation represent? It's a residual, which is like what it actually costs to make that pizza versus what it will be predicted, right? So if my R squared value is 0.867, I'm saying 86% of the variability in the cost of the pizza, meaning how much it is above or below or the line, is accounted for by the least squared regression line. Meaning these differences here are the variability. 86% of the variability is accounted for by the least squared regression line, meaning that they're close or far away. Closer or farther away would mean that if I've got values that are way up here, is my R squared value going to go up or down? Okay? So the amount of variability, how far they are from the least square regression line, is accounted for by the R squared value. So what it's saying is this particular value talks about how good my least square regression line fits my data. Take the square root of this value. What do you get?
2931.
Okay. So that's a pretty good correlation. Let's just say for a second, I added in these two toppings here, and all of a sudden, I had an R squared value of, let's see. Let's go the other way. Let's say I add these in, and all of a sudden my least squared regression line, it's got a correlation of 0.643. Square 0.643.
0.413.
So as my correlation goes down, less of the variability is accounted for by my least squared regression line. That makes sense? So now only 41% of the variability is accounted for by the least squared regression line. So the less closely linearly associated things are, the more variation there is, which means less of it is going to be accounted for by the least squared regression line. Does that make sense? Because the least squared regression line seeks to minimize these distances, but if the distances are great because the discrepancies are there, there's outliers, less variability is going to be accounted for. That makes perfect sense, doesn't it?
Wait, so the greater R squared is, the lower the amount of variability of the residuals from the line?
The greater percent of variability is accounted for by the least squared regression line.
Yeah, but like, that's what it means, right? Like if you have a greater R squared value, then like that means like the line, like there's less residuals, like they're like not as far.
That's right.
Okay.
They're closer to the least squared regression line. So being accounted for by the least squared regression line means if there's a higher percentage, that means more of the variability, meaning the least squared regression line is closer to the values. The residuals have a smaller standard deviation. Okay? All right, so here's the thing. This is one of, it's a challenging concept. So to reinforce that, we're going to back it up by going on to the next lesson. It's going to help reinforce this. So I would like for you, let's do this. I'm going to pause this for a second because I'm going to have you go do something. I'm sorry. All right, so here we go. Let's walk through these notes together here and talk about the top.
Yeah, for sure.
So do a sketchity sketch here. Here's what we've got. This represents our least squared regression line. I'm going to label it LSRL, and I'm going to put in some just general data points here. What we did was we drew in our x, our mean of our x, and we drew in the mean of our y values. You need to think of this point right here as a seesaw. Okay? The least squared regression line is going to tip on that point. I'm going to erase this because that's just frankly confusing. What is this, economics? Okay? And so we've got, I've seen those graphs. They're intense, right? They got a lot of lines on them. But basically what we're saying is when I put a point here, when I put a point down here, this thing seesaws toward it, right? I put a point up top, it seesaws toward it. The least square regression line is a tipping. This is what Gigi was trying to ask, was like, why is it moving? It's going to seesaw toward the points. Well, a good least squared regression line has a low S. What does that mean, low S? It's got a low standard deviation. Because the more closely the points are associated together, the less residual there is. The less residual there is, the less standard deviation there's going to be. It's like test scores, right? So if I say, hey, the standard deviation on the last test was 2%. Wow, everybody's concentrated. Now that doesn't tell me if everybody did well. That tells me everybody did the same, relatively. So if my mean is 50 and everybody got within 2 percentage points of that, I'm not feeling great about that. I'm feeling consistent about that. Okay? I'm not feeling good about it, but I'm feeling consistent, right? But it also has a high R squared, meaning it accounts for a lot of the variability in the data. Meaning it's close to a lot of things. It accounts for that variability. All right, so here are some general things. Least square regression line. Y hat, we know, is equal to B sub 0. This is another way to write this. This is what's going to show up on your formula sheet. B sub 0. But Mr. Sayers, I don't know what that is. Yeah, you do. It's a y-intercept. It's just another way to write it. Plus B sub 1 times x. B sub 1 is my slope. Here's what's cool. Sorry, wrong. Rise over run.
What is that B1?
Say what? Okay, so check this out. In our least squared regression line, okay, our slope is equal to our R value times the standard deviation of y over the standard deviation of x.
How do we find those?
Great question. Actually, what happens is they're going to give you these values and ask you to write the standard or write the least squared regression line. Okay, so we're going to have what's called a mini tab output. A mini tab output is basically a computer printout of all this data, and they're going to say, "Hey, what's the least squared regression line?" You're going to be like, "I'm out," but now you know. Okay, but now you're going to know. And so here's another. B sub 0. So our y-intercept is equal to y bar, so the mean of y minus b1 times the mean of x.
Okay.
Go down to number 2, down below. You're going to see how this works. So instead of having you draw in all these lines and things like that, I want to fast forward to the point where we're using these calculations. So here's what a particular problem might look like. So they'll say, we collect data from a random sample of 15 high school students to investigate the relationship between foot length and height. So are people with bigger feet taller? Okay, great.
No.
The mean and standard deviation of the foot lengths are x bar is 24.76, and the standard deviation of x is 2.71. Pretty standard stuff there, right? Unintended. So the mean and the standard deviation of the heights is, the mean height is 171.43, the standard deviation of y is 10.69. The correlation between foot length and height is r is equal to 0.697. So interpret that real quick for me.
So you have to like do
No. Interpret this for me. I've given you the r value. Roughly positive.
Roughly strong.
moderately.
No. Moderate is a better word. Moderately strong,
Positive.
positive linear association between foot length and height. So there's a moderately strong positive linear association between foot length and height, which in general means it's kind of true that people with bigger feet are taller. Is it really, really, really true? It's moderately true, right? Because it's about 0.7, so it's not bad. So find the equation of the least squared regression line. This is the new stuff. All the rest old stuff. Look at all this old stuff. Here's the new stuff. So here's what we're going to do. Write out the equation. Y hat is equal to B sub 0 plus B sub 1 times x. So B sub 1 is my slope my slope is equal to my R value times the standard deviation of y over the standard deviation of x. B sub 0, which is my y-intercept, is equal to the mean of y minus the slope times the mean of x. Where am I going to get all these values? Hello, given, right? So my b sub 1, which is my slope, is equal to 0.697 times standard deviation of y, which is 10.69 over 2.71.
What are the two numbers in the fraction?
Standard deviation of y and standard deviation of x.
No,
But,
like, what are they?
But what's that?
Like, what are the numbers?
10.69 is the standard deviation of y. 2.71 is the standard deviation of x.
Is that on our formula sheet too? The R.
This is on your formula sheet.
Thank God.
This is on your formula sheet. So what I'm doing right now is I'm giving you information that is going to help you in the future go, I don't know what the heck I'm looking at. I got all these letters and numbers. Well, now you know. Now you know. And so this is 2.75. So in general, if I'm talking slope, that would be as foot length increases. For every centimeter that foot length increases, height increases by 2.75 centimeters. So then my b sub 0, I'm going to do a little calculation here, right? Because I'm going to say b sub 0 is equal to, and I've got y bar, so that would be 171.43 minus 2.75 times 2.71. Not true. 2.75 times 24.76. What do you get for b sub 0?
103.6.
103 point what?
65.
I got 3.4.
Me too.
What'd you get?
3.4.
3.4. An answer you do not have. You don't have the answer yet. Your answer is y hat, so predicted y value is equal to, you got to put all the pieces together. 103.34 plus b sub 1, which is 2.75, times x.
Do you have to do the context for it?
No, not for this, but you could. So predicted height is 103.34 plus 2.75 times foot length. What if I asked you, what is the r squared value for this? How would you find that? Square the r. And then you'd say, do that. Square it. Do that. I'm going off the cuff here. I love it. What'd you get? 0.4856?
0.486.
So 48.6% of the variability in height is accounted for by the least squared regression line.
That's not good.
Well, what was our correlation?
697.
0.697. Remember, 0.486 is like, oh, 50%. What was 50% on our scale of -1 to 1? 0.5 was like moderate, right? So 0.5 was moderate. So if I think about it in terms of -1, -0.5, 0, this is weak. So 0.5 is moderate. So if I've got 0.486, that's a moderate amount of variability accounted for. All right? Hey, so 3.2 homework, finish that up. I've got a bunch of review materials for you for next time, and we're going to do test corrections. All right? All right, guys.
Wow, that was a lot.